Welcome back. Welcome back to our statistical learning session. Today, we'll be talking about hypothesis testing. Yesterday, we talked about notation modeling, and today, we'll talk about setting up the hypothesis testing using notation modelings. What we're going to do is we're going to set up a framework in a mathematical language such that we can decide whether the medicine is effective than a placebo. How do you do this? In null hypothesis, we want to see whether difference between whether difference between delta C and delta D is equal to 0. That's what we know, right? In null hypothesis, that's a status quo. Let me set up my pen here. In null hypothesis, we want to know whether in null hypothesis we want to know whether difference between delta D and delta C is equal to 0. That's null hypothesis. And in alternate hypothesis, we want to know whether delta D is greater than 0. What does it mean? We are saying that delta D is equal to delta C. There is no difference between whether it's a placebo or whether it's a drug in lowering the cholesterol. And we are saying that in alternate hypothesis, delta D is actually greater than delta C. Or delta D minus delta C is greater than 0. Its difference is greater than 0. That's what we're trying to compute here. For this, since our data is in Gaussian, we don't need to use the CLT. Even though so, we'll use some parts of CLT so that it is easier for us to compute the sample average of distribution of sample average of sample distribution of sample average of X and Y. How do you do that? Let me show you. For Xn, we know X is a X1 through X in here is a Gaussian. We know that from our previous exercise. We know that is a Gaussian. That has a this kind of variation. Now we'll take the central limit theorem anyway, such that it helps to get what we need. We'll take the sample average of this of Xn and subtract the mean from it, and then we will divide by standard deviation and multiply by square root of n, and this should be equal to the normal standard. We know this, right? Therefore, because of this expression here, we can say that xn is equal to what? Before we do that, let me do more calculation because it needs more calculation here. This is equal to, we can multiply by xn here, xn d, we multiply by on both sides, and therefore multiply by square and multiply by square root of sigma square d on both sides, which will give us 0 square d. In the same way, we will multiply by square root, divide by square root n on both sides, which will give us n. And next step, we will add delta d on both sides, which will give us delta d, and this is what we need. Therefore, the sample average has a distribution of delta d and variance of square root of square root of sigma, root power of sigma to power to sigma, and divided by n. In similarly, we can say that ym, which is the sample average of y, have the distribution of n, and since it's a control, it will be control c, and 2 to power of sigma of c divided by m. That's how we get our distribution of sample average of x and sample average of y. Now, we are trying to make the test of the expected value of our sample averages. Therefore, we'll be working with our sample averages. What I'm as a farmer as a data scientist, what I'm trying to test here, we are trying to test whether the difference between delta d and delta c is zero or not. That's what we are trying to test here. Therefore, delta c and delta d is our mean, but in reality, we have our sample averages which represent delta c and delta d. Therefore, we'll take the difference between xn and ym and subtract the delta d and delta c. But this is not still the standard normal. To make it standard normal, we have to divide by the variability of xn and ym. And what defines the variability? This variances defines our variability here. And since x and y are independent, we can sum the variances, take a square root of that, and divide it to get the standard normal deviation, to get a standard normal for what we need. Dividing the x and ym minus xg and minus delta d and minus delta c by variances, this should give us the standard normal. This is all we need for our this slide. In end, let me quickly summarize what we learned today. We learned about setting up the hypothesis testing, alternate null hypothesis, and alternative hypothesis using mathematical expression. For that, we use delta C equal to delta D as our null hypothesis and delta D greater than delta C as our alternative hypothesis. Then we went ahead and calculate the standard distribution of sample average of x and sample average of y using central limit theorem. But for this situation, we do not have to take asymptotic of our central limit theorem because these are already Gaussian. That's why it was directly equal to standard normal. Instead of being being instead of being instead of this being instead of this being asymptotically standard normal, this was actually a standard normal since they're already Gaussian format. And then we went ahead and took step toward getting a test statistics, which was our difference between sample averages and sample and actual means, that is delta C and delta D, and we took the difference between those two to see whether it is greater. We took difference between those two and try to represent that in a standard normal format, and this will be later used as our test statistics to determine whether delta C is equal to delta C is equal to delta D or not. That's much for today. I will see you next learning session. Thank you so much.